Howdy, in this video we will look at section 7.3 of the Subson Hill textbook, Axioms for Zero, as we build a simple mathematical system. In section 7.1 we develop the commutative axiom, namely for all x and for all y, x plus y is equal to or identical with y plus x. And this is just a basic property of addition. 3 plus 2 is the same thing as 2 plus 3. We also developed some definitions. We defined the number 2, the number 3, the number 4, the number 5. But as an alternative to the Subson Hill textbook, we could have the infinite set of all integers. That is -3, -2, -1, 0, 1, 2, 3, etc. in both directions, positively and negatively. But in fact, in the next section of the Subson Hill textbook, we will have or develop an axiom for negative numbers. So we can think about not just the definition of a few numbers, but we can think about a set of all integers, and that's a set of infinite numbers. And when we do that, we actually will have in abstract algebra a so-called group. Now in section 7.2 we developed the associative axiom. Addition is a binary operation. In that sense, we might think of it as just adding two numbers. But what if we have x plus y plus z? If we're going to keep it as a binary operation, we can add parentheses. But there are two ways to do that. We can group the x and y, or we can group the y and z. So in other words, the associative axiom is for all x, for all y, for all z, parentheses x plus y close parentheses plus z is identical with x plus parentheses y plus z close parentheses. Now presently we will develop the zero axiom. We know, for example, that 4 plus 0 is equal to 4. Add 0 to any x, any number x, and the answer will be x. Hence in general x plus 0 is equal to x. And in algebra this is called the addition identity property. So now we have our zero axiom. For all x, x plus 0 is equal to x, or is simply identical with x. Note in algebra there's also the multiplication identity property, namely 1 times x is equal to x. But in our case, we're only going to think about addition in the simple mathematical system. And with this toolbox, we can do some further proofs as we develop this system. With all of that said, let's do some proofs. We'll derive some theorems. We have a toolbox, and within this toolbox, we have some axioms, some definitions, and finally, at least implicitly, various theorems, although I don't explicitly list them here. For example, a theorem before 23, insofar as we have proved that theorem, it becomes part of our toolbox as a premise, and as a premise we can use it in further proofs. For example, if we prove theorem 23, we can then perhaps use it as a premise to prove theorem 27, or whatever. Now this time we have three axioms. We have the commutative axiom, the associative axiom, and the zero axiom. That's really the only thing that's new, although I suppose we have additional implicit theorems. Moreover, because we're using various rules of inference in our proofs, we have to remember those inferences. And the main one here is the rule of identity, because, so to speak, we can then substitute different things for different statements. So if we say that 2 is identical with 1 plus 1, we can substitute a 2 in for each time we see 1 plus 1. Or the other way around, if we see a 2, we can place in a 1 plus 1, and so on and so forth. And then we also have the logical truth rule, where we can state various tautologies. So let's do that. Let's look at theorem 23 and prove it. We're told that we want to prove that parentheses 1 plus 0, close parentheses, plus 0 is equal to 1. So how can we do that? We're definitely going to have to use the zero axiom. But even before we do that, I suppose we could look at this left-hand side. It's very long, so why not use the logical truth rule? Because then if we say that this left-hand side is identical to itself, the only thing we have to, so to speak, work with or work on is the right-hand side. So let's do that as the first step. And so for line 1, we'll say that parentheses 1 plus 0, close parentheses, plus 0 is equal to parentheses 1 plus 0, close parentheses, plus 0. And that's a logical truth. It's a tautology in the sense that something is identical to itself. But now we can resort to that 0 axiom. For all x, x plus 0 is equal to x. And we'll substitute 1 in for x. Hence for line 2, we'll just say that 1 plus 0 is equal to 1 by the universal instantiation of the 0 axiom with x being equal to 1. But now we can use the identity rule. Just look at lines 1 and 2. Because we're told that 1 plus 0 is identical with 1, here we have a 1 plus 0. We can just substitute in, so to speak, a 1 there. In other words, for line 3, we can get parentheses 1 plus 0, close parentheses, plus 0 is equal to 1. Okay, so 1 is going in for that 1 plus 0, and then we have this plus 0. So that's the identity rule with lines 1 and 2. And then finally, with lines 2 and 3, we can get what we desire. For line 4, therefore, we have parentheses 1 plus 0, close parentheses, plus 0 is equal to 1. Why? Because we have the identity rule with lines 2 and 3. Because we have this 1 plus 0 on line 3, but we know that is identical to 1 according to line 2, hence the right-hand side, we can say 1. So that proves theorem 23. But what about theorem 27? We have 3 plus parentheses 0 plus 0, close parentheses, is equal to 3. I suppose there are different ways to go about these things, but this time I'm going to jump into the 0 axiom right away. So let's just say for line 1 that 3 plus 0 is equal to 3 by the universal instantiation of the 0 axiom with x being equal to 3. And then for line 2, what I'm going to do is this. I'm going to say that parentheses 3 plus 0, close parentheses, plus 0 is equal to 3 plus 0, that's in parentheses, plus 0. That's a logical truth. We're good to go. And so in this case, we're definitely going to have to do some regroupings, though, because of line 2. So that means we're going to have to resort to the associative axiom, at least eventually. But for line 3, we can now use the identity rule with lines 1 and 2. That is, we can say that we have parentheses 3 plus 0, close parentheses, plus 0 is equal to 3 plus 0 by the identity with lines 1 and 2. Because we know on line 1, it tells us that 3 plus 0 is equal to 3. Line 2, we have this 3 plus 0. Hence, so to speak, we can substitute in a 3 for that 3 plus 0. What about line 4? We can use the identity rule once again, this time with lines 1 and 3. We have parentheses 3 plus 0 is equal to 3 by the identity lines 1 and 3. Because we have this 3 plus 0, but once again, 3 plus 0 is just 3 according to line 1. Hence, so to speak, we can substitute 3 into that right-hand side. But now, because we want the parentheses grouped up correctly, we can use the associative axiom. So let's instantiate that with x being 3 and y being 0 and z being 0. So we have parentheses 3 plus 0 is equal to 3 plus, and that's in parentheses 0 plus 0. So this is just the universal instantiation of our associative axiom. X is equal to 3, y is equal to 0, z is equal to 0. And now we have everything we need, because we can say, therefore it follows that we have 3 plus in parentheses 0 plus 0. And on the right-hand side, we have 3 by the identity rule with lines 4 and 5. On page 257 of the Substance Hill textbook is a very simple, straightforward exercise. The textbook tells us that the axiom for 0 is sometimes described as asserting that 0 is a right-hand identity element for addition because adding 0 to a number gives an identical number as a sum. In other words, x plus 0 is equal to x, and that's obviously a true statement. The question here is which of the following statements are true? One of the big things to notice is that each of these statements is a universal declaration. We have for all x, or in other words, for every x, for every x, for every x, for every x, for every x. If you can find one contradictive example to a universal statement such as this, that's sufficient to say that statement must be false. In fact, the first statement is false because we're told that 0 is an identity element for multiplication. That is, for all x, x times 0 is equal to x. Well, that's clearly false. For example, if x is equal to 1, we have 1 times 0, but that does not equal 1. And this one example contradicts this universal claim, and that's sufficient to say that universal claim cannot be true. And that's one of the main lessons here. For number 2, we're told that 0 is a right-hand identity element for subtraction. In other words, for all x, x minus 0 is equal to x. Here we do have a true statement. Number 3, 0 is a left-hand identity element for subtraction. For every x, 0 minus x is equal to x. Well, obviously that's false. If x is equal to 5, we would have 0 minus 5, but that does not equal 5. This one contradictive example is sufficient to say this universal statement is false. Number 5, 1 is an identity element for addition. For all x, x plus 1 is equal to x. Again, that's obviously false. Number 6, 1 is an identity element for multiplication. For all x, x times 1 is equal to x. This is true. It's now a good time to conclude this video. Up next is section 7.4, axiom for negative numbers. This will allow us to have a set of the integers, and that is an infinite set of infinitely many numbers. And with our various axioms, we will then have what's called a group in abstract algebra. In this case, we'll have an abelian group. So that's coming up, section 7.4, and I'll see you then.